Hey, today I'd like to look at an especially important power series that you're going to see quite a bit of and that will motivate much of what comes next. And it's this power series here that we've looked at once before, the sum n equals 0 to infinity of x to the n over n factorial, which is 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the fourth over 4 factorial, etc. Don't let those first few terms confuse you into thinking that there's something special going on there. The 1 is x to the 0 over 0 factorial, where 0 factorial is 1. The x is x to the first over 1 factorial. And the x squared over 2, well, 2 factorial and 2 are the same number. So it's the same pattern throughout. It's just that I've simplified the first few terms. And the last time we looked at this series, we used the ratio test to determine that the radius of convergence of the power series is infinity, meaning that it's defined for all real numbers, or this power series defines a function whose domain is all the real numbers. And if you need to remind yourself or convince yourself, can't hurt to take a moment, use the ratio test, find the radius of convergence for this power series, and then start the video back up. Otherwise, if you remember or you just want to take my word for it for now, we're just going to keep on going and assume that you can compute that the radius of convergence of this power series is infinity. Here's where the fun begins. Take the derivative of this power series by taking the derivative term by term, which we have a theorem that says we're allowed to do. So take a moment, see if you can work that out, pause the video, and when you've figured it out, start it back up. And when you do that work and you take a moment and you simplify the results, you find out that the derivative of this power series right here is exactly what we started with right here. In other words, this power series is its own derivative. And you say to yourself, when is a function its own derivative? And that's a great question, and it turns out that that question can be phrased as a differential equation. For what function y does the derivative of y equal y? Well, the beautiful thing about this differential equation is that it's separable, and so we can solve it. So take a moment, pause the video, solve this differential equation, and when you're done, start the video back up again. And when you separate the variables and then integrate, you get that the natural log of the absolute value of y is equal to x plus c. And then raising e to both sides, you get that e to the natural log of the absolute value of y is e to the x plus c, and e to the natural log of the absolute value of y is just the absolute value of y. And e to the x plus c we usually write as e to the x times e to the c, and then recognize that e to the c is just a different constant, and so we can write it like this. And since c can be positive or negative, we get that y is equal to c e to the x, meaning we can drop the absolute values because c is either positive or negative. And that was sort of a review of the standard maneuvers in differential equations. We've seen them many times before, and we've found that this function y is some constant times e to the x. Well, it would certainly be nice to know what the constant is. And if we take a look at the power series here and give it a name, f of x, it's not hard to see that f of 0 is equal to 1. All the terms with the x's in it go away, and we just get the 1 that is the first term of the power series. And this function f of x is the function y that we are trying to find, the function that is its own derivative. And so we have some initial conditions that we can apply. In particular, when x is 0, y is 1, and so 1 is equal to c e to the 0, meaning that c is equal to 1. And that gives us our final answer, that y is equal to e to the x. And what did we just determine? We just determined that this power series, sum n equals 0 to infinity of x to the n over n factorial, is equal to e to the x. Or to put it another way, I know this doesn't really say anything different, but it's sort of a different way of looking at it or thinking about it. E to the x is the power series sum n equals 0 to infinity of x to the n over n factorial. And as we determined, this is true for all real numbers x. For example, what is e to the 7th? Well, e to the 7th is 1 plus 7 squared over 2 plus 7 cubed over 3 factorial plus 7 to the 4th over 4 factorial, and on and on and on forever. If you added up the first billion terms of this series, you would come up with something very, very, very close to e to the 7th, but it wouldn't be exactly e to the 7th. If you want exactly e to the 7th, you need all infinitely many terms, which you can't add infinitely many terms, but you can take the limit as n goes to infinity of the nth partial sum of these terms, and that would be exactly e to the 7th. Okay, I hope you appreciate how cool that was. We just found a power series for e to the x. As I mentioned at the beginning, this will motivate where we go next. See you soon.